In Chapter 2, Section 6, we'll look at limits and infinity. So the first problem says, evaluate the limit as x approaches 0 from the left, that's what that little minus means, of e to the 4 divided by x. So let's actually go to Desmos and we will plot this curve. So it was exponent, which is exp, parentheses, and it was 4 divided by x. Okay, let's make sure I have that right. E to the 4 over x. Okay, that's correct. So e to the 4 over x. And as you can see, there is a asymptote at x equals 0 because you can't divide by 0 in an exponent. So 4 divided by 0 would be undefined. So there is an asymptote there. But as I approach 0 from the left, the y value is getting smaller and smaller and approaching 0. Okay, so we can see it there on the curve. So if we let t equal 4 over x, we know that t approaches as t approaches negative infinity as x approaches 0 from the left. Therefore, the limit e of x equals 0. So basically what they're trying to say is, if you set up t like this is 4 over x, then as you make x smaller and smaller, t will get bigger and bigger. So imagine you're dividing 4 by a really small number. Well, that's actually going to make t get bigger and bigger. So if this x bigger and bigger negative, I should make sure I comment on that because you're using negative numbers. So if t is a large negative number, then e will actually become, let me write some of this instead of just saying it. Okay, so we have e to the 4x. And they say let t equal that exponent. And then they say as x approaches 0 from the left, so it's negative numbers, but they're small negative numbers. So imagine you take 4 and divide by negative 0.0001. Well, that's actually going to give you negative, let me do the math real quick. Should be like 4,000. You get 40,000, so you get negative 40,000. Now plug that into the exponent function. So if you type in your calculator e to the negative 40,000, I mean, actually there's probably no point in doing this. It's going to be 0. I mean, my calculator just straight up says 0. But if you picked even smaller numbers, like even a bigger number, if you pick this x value is 0.1, you'll get negative 40, and e to the negative 40 is like a tiny, tiny number. So basically they're just saying that this function is going to approach 0, as we saw in the picture, in the Desmos. So you can either think about it algebraically like I've written here, or you can look at the graph and you'll get the same result. Okay, for problem 2 it says find the limit if it exists. If an answer does not exist, enter does not exist d. Okay, so when we have the limit as x approaches infinity of 9x minus 4 over 2x plus 9, the first thing you want to do is see if anything factors or cancels. Now there is no common, so if I look at the numerator, there's no common number between 9 and 4, so I can't factor anything out there. Look at the denominator, there's no common number between 2 and 9, so I can't factor out anything there. Then I'm going to prove this with a table. So let's say x is approaching infinity. So let me pick larger and larger values of x, and then we'll calculate 9x minus 4 over 2x plus 9. Okay, so let's say we pick 1, 10, 100, and 1,000. That's probably enough right there. If you plug 1 into this, you get 9 minus 4 over 2 plus 9, which is 5 over 11. And I'll just leave it like that. Let's say you plug in 10, you get 90 minus 4 all over 20 plus 9. Well, this would be 86 over 29. Now let's say we pick 100. You would get 900 minus 4 over 200 plus 9. And that's going to equal 896 over 209. Then we plug in 1,000. We're going to get 9,000 minus 4 over 2,000 plus 9. Or this is 8,996 over 2,009. And what we're noticing is that, or what we should notice is that these numbers, this number is almost 90 over 30, 20, we'll put it as. This is like 900 over 200. This is close to 9,000 over 2,000. So my argument is, and I probably couldn't have rounded this one down to 20, I should probably call it 30. I guess I can write it as 30. But I can cancel those two zeros, and this is like 9/3. I can cancel these 4 zeros, and this is like 9/2. I can cancel all 3 of those zeros on top and bottom, and this is like 9/2. And what we're finding is that x gets bigger. As that gets bigger, this is getting closer and closer to exactly 9 over 2. So there's an easy way to do these problems. You can basically ignore anything that doesn't have the highest power of x on it. So all we have to do is come into this problem and say, guess what? As x gets big, this 4 doesn't matter anymore. As the x gets big in the denominator, this 9 doesn't matter anymore. And we can simplify this to just the limit as x approaches infinity of 9x over 2x. But now, since there's no other numbers getting in the way, you can cancel this x with this x, and it's going to simplify to the limit of 9 over 2, which is just 9 over 2. So the limit is going to be 9 over 2. So you can do these problems pretty quickly because you might notice, hey, it's just the number in front of this x and the number in front of this x. So as long as they're lined up, and even if they're not lined up, just throw out any numbers that don't have an x, and then the x's will cancel, and it's the coefficients of the x's that are going to matter. Okay, we're going to use the same idea for problem 3. So it says find the limit if it exists, and then put d and e if it does not exist. Okay, so in this one, I'm going to show you another way to do it. Do I want? No, I'm not going to. Let's keep it the same way. So we have the limit as x approaches. There is more than one way to do this. There's 3 ways to do it, and I showed you 2 in the last problem. Plug in numbers and then cancel the highest power of x. There's another one where you divide by the highest power of x, but when you have a square root, it can be confusing. So we have x plus 7x squared. And on the bottom, we have 3x minus 1. Now I'm going to compare the top and the bottom separately, and I'm going to say 7x squared is going to grow really fast, because when I start squaring x, I get numbers like 10 becomes 100, 100 becomes 10,000, etc. So those numbers are going to grow so fast that this x is not going to matter. So let's get rid of it. Then I'm going to look at the bottom. This 3x is going to grow so much faster than 1, which is constant, that this minus 1 is not going to matter. So we're going to change this to the limit as x approaches infinity of just the square root of 7x squared divided by 3x. Now, because there's no other numbers or letters in the way, I can apply the square root and make it square root 7 times the square root of x squared all over 3x, and I should have the limit in front of it, but just to save time I won't write it. Okay, then this square root x squared will just become x, so we get, I'll write it now I guess, the limit as x approaches infinity of x times the square root of 7 over 3x. And now we can say This x will cancel with that x. They'll divide each other out. And so we get the limit of root 7 over 3, which is just a number. So it's just going to be root 7 over 3. Little more complicated because it's kind of hard to see. You can't just grab the 7 and 3 like maybe we did in the last problem. You have to make this argument that the square root will actually simplify. Okay, for 4. Okay, so for 4, I have the limit as x approaches infinity of the square root of x squared plus 5. And I can do the same argument. I can say this 5 is not going to matter as x gets big. So we really have the limit as x approaches infinity of the square root of x squared. Now that square root and that x squared will cancel, so you have the limit as x approaches infinity of the function x. Well, what is the function x? The function x is a straight line at a 45-degree angle that looks like this. And it goes off like that. As x gets really, really big, so as I go to the right, so I'm going to the right, what is my y value doing? It is getting bigger and bigger and bigger. So it is going to positive infinity. So in this one, I couldn't cancel anything and get a nice number. So this one would be infinity. So it's just going to grow and grow and grow. Okay. For problem 5, we'll do a similar analysis. We have the limit as x approaches negative infinity, so the x values are growing to the left, negative values, of x squared plus 2x to the 5th. Now x to the 5th is going to grow so much faster than x squared that I don't even need to worry about this x squared. So we're going to have the limit as x approaches minus infinity of simply 2x to the to the positive 5. Okay, now we have to think about the power. So as you have negative numbers here, so we're putting in large negative numbers raised to the 5th power. Because this is odd, the minus will stick around. So odd powers with negative numbers, the minus sign will stay. So this is going to equal minus 2 times some big number. And we're going to call that some big number infinity. And 2 times infinity is still infinity, but there's a minus sign in front of it. So we're going to get minus infinity. Okay, and actually let me show you a little more for that. So let's say I just want to think about 2 times x to the 5th. All odd powers look like this. They go down, they go through the origin, and then they go up. So as x gets bigger, this goes to positive infinity. As x gets more negative, it goes to negative infinity. And that's the trajectory we're on. So x approaching negative infinity right there, we're actually going this way. And as I go that way, I have to be on this curve, and the y value is going down to minus infinity. So that is a graphical representation of 2x to the 5th. Okay, problem 6, it says find the limit. Well, let's write it. Find the limit x going to positive infinity of 5 minus e to the x divided by 5 plus 7 e to the x. And e to the x is going to dwarf any kind of constant. So e to x grows really fast, so this 5 isn't going to matter, this 5 is not going to matter. I need the 7 still. So this is going to simplify to the limit x approaches infinity of negative e to the x divided by 7 e to the x. Now it doesn't show up, but I'm going to write a 1 in here just so it's a little easier to see. 1 times e to the x is still e to the x, so I can do that. And because we're using multiplication, there's no other terms, we can say e to the x on top will cancel e to the x on bottom. So this limit will simplify to minus 1 over 7. Okay, so it's all the same kind of approach. Anything with an x in it will stick around, and you can toss out everything else. Okay, for 7, actually let me make up one just so we can be clear on this. Let's say I have limit as x approaches infinity of 4x to the 4th minus 3x to the 3rd plus 2x to the 2nd plus 107x minus 20. All divided by, let's do 5x to the 4th plus 17x 3rd minus 20x squared minus 53x, I'm making this up as I go, plus 17. You can literally cross off everything except for the biggest power of x. So I can prove that as x gets bigger and bigger, we're not going to care about any of that or any of this. We just care about the x4 term. So this is going to be the limit x approaches infinity of 4x4 over 5x4, and once again x4 cancels x4 and the whole thing will reduce to just 4 over 5. And this is, I should have mentioned this, this is called a horizontal asymptote. So in our graph, we find the y value, 4 over 5, let's say it's right there, and we put a horizontal dashed line in it that goes through that point. What it says is the function might cross this point for small values of x, but for large values of x, our function, whatever it looks like, is going to approach this line and kind of flatten out towards that line. Even on the left side. Not sure what the function looks like, but it's going to eventually flatten out towards that dashed line. Now again, for small values of x, it might cross it, it might do stuff in here, but for large values of x negative or large values of x positive, it will start to flatten out towards that dashed line. Okay, so that's a little more theory on what's going on here. Okay, in problem 7, they want us to find just that, horizontal and vertical asymptotes. So vertical asymptotes we'd already seen, it's the values that create the denominator to be 0. Okay, so let's start with the vertical asymptotes. Call them VA. VA occurs when the denominator x squared plus x minus 12 equals 0 because we can't divide by 0. And it turns out this function will factor into x plus 4, x minus 3. Well, there's two values of x that make those two bubbles 0. One is negative 4 and one is positive 3. So those are going to be vertical asymptotes. So I'm not entirely sure what this thing looks like, but I know at 4 and positive 3, we're going to have two vertical lines. And our function cannot touch those lines. It cannot go through them. Now, it could end up on both sides of it, but it cannot touch those lines because that would create a divide by 0 error. Okay, so we just have to write the smaller x value is minus 4 and the larger x value is 3. So that gave us those two answers right there. Okay, now it wants us to find the horizontal asymptote, and that's where we're going to use what we just learned of letting x go to infinity. So for our horizontal asymptote, we're going to take the limit as x goes to infinity of that function And by that argument I just made, we can toss away everything except for the x squared terms. So that's gone, and that's gone. So we're going to get, this would be the limit as x approaches infinity of 9x squared divided by 1x squared. And those x squareds can now be canceled because there's one on top, one on bottom. And this limit equals 9 over 1, which is just 9. So at the height, y equal to 9, we will get a horizontal asymptote that looks like this. And then we would have to plug in x values to see where the function is. Let's actually go to Desmos and see this one so we can see what this will look like. So all you have to do is put y equal to 9 for this answer here. But let's go see this in Desmos. Okay, so we have our function here in Desmos, and we can see that we have these vertical asymptotes at -4. So notice this is approaching -4 in the x direction. This is approaching -4 in the x direction. And then we have another one at +3. So as I'm moving this to the left, notice that first number is getting closer and closer to 3. As I'm moving this to the right, the first number is getting closer and closer to 3. And then here, it's going to get closer and closer, the y value, to 9. So 9.3, 9.3, 9.275, etc. And on this side too, 8.8, 8.85, 8.6, 8.6, and then it's getting bigger and bigger, closer to 9. So that's where the horizontal asymptote is. Okay, same approach with number 8. I won't graph this one since I think you got the idea now. We have y equal to, I'm going to rearrange this a little bit, x to the 4th plus 2 over -x to the 4th plus x squared. And for the vertical asymptotes, that occurs when -x to the 4th plus x squared equals 0. Or I can factor out an x squared. I wish I didn't rearrange this now. It's okay. Factor out an x squared, and you will get -x squared plus 1. That has two solutions when x squared equals 0 or x equals 0. Square root 0 is 0, so square root both sides, x equals 0. Or -x squared plus 1 equals 0, which says 1 equals x squared. So move this term over here, it becomes positive. Take a square root out of plus or minus. Square root of 1 equals x. Square root of 1 is 1, so plus or minus equals x. So there's three asymptotes: -1, 0, and +1. Vertical asymptotes. Three things that make that denominator go to 0. Okay, for the horizontal asymptote, we can come back here and just say, okay, x4 dominates on top, -x4 dominates on bottom. So this whole thing is going to simplify to x4, 1x4 over -1x4. Those x4s will cancel now. And we get this whole function will simplify to just 1 over -1, which is just -1. And so we get y equals -1 would be the horizontal asymptote. Okay, problem 9. How large do we have to take x so that 1 over root x is smaller than 0.0001? Okay, so we have 1 over square root x must be smaller than 0.1231. Okay, so first we're going to take the reciprocal of both sides. So we're going to flip this side, and we're going to flip this side, which means this is right now on top of 1. Now we're going to put it below 1. And then we'll get square root of x has to be smaller than, if you take, I thought I had this written down, I guess not. If you take 1 divided by 0.001, you will get 10,000. 10,000. Now to get rid of square root of x, we have to square that, but that means we have to square this side. So we're going to get x has to be smaller than 10,000 squared, which is 10. Let's count. 1, 2, 3, 4, 5, 6, 7, 8. It's 1 with 8 zeros. It's 4, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 100 million. So if x is 100 million and we take 1 over the square root of x, our answer should be smaller than 0.00001. So oftentimes this is used in tolerances, or so you pick your error. So you say, okay, I want my error or my tolerance to be smaller than some number. So let's say I'm producing turbine blades for an airplane, and I want their thickness to be such that they can't be smaller than some. The difference in what I want the thickness to be and what it actually is has to be smaller than some number which I pick called the tolerance. And then I can do a calculation like this to figure out, okay, how accurate or how much effort do I need to put into my machine that makes the turbine blade so that the things will come out within the thickness I need them to be. So that's kind of an application of when we might do something like this. Okay, last problem in here, find the limit if it exists. If an answer does not exist, put D in E. The limit as x approaches infinity of 7 cosine x. So this one, it helps to recall what cosine x looks like. Here's x, here's y. If you put a 7 in front of cosine x, it will now bounce between 7 and -7. And cosine starts at 7, goes to 0, down to -7, back to 0, up to 7, and then it's just going to repeat this forever. So as x goes to infinity, there is no limit because the y value will never hone in on one value. So the idea of the limit is that your y value will flatten out to some value. Well, this will never flatten out. We'll just keep going and going and going. It will bounce between 7 and -7, so therefore the limit does not exist. So the picture hopefully helps you see that answer. And that will complete section 2.6.